about how people are using raster data. Also, that's my background. I think the other sort of like large component is the sort of czar netcdf climatology data sets, doing a lot of work on the cloud. And so as these formats sort of advance and become more cloud optimized, we're exposing more and more different types of data.
I just want to clarify, when we talk about cloud optimized, are we talking about streamable data?
Yeah, streamable data where you can host the files in blob storage, and there's a way to get only the bytes that you want. If you're dealing with large sets of data, often they're like large files or many small files, there needs to be a way to only read the bytes that you want, or else you have to download the entire, set of data into your local machine, which oftentimes is not even feasible depending on the size of your machine. So when it's cloud optimized, it means that it's optimized for reading windows or pieces of that data set that is hosted on the cloud, and you're not really reading anything you don't need to.
When we talk about reading, so I think for cloud optimized GeoTIFFs, for example, we're talking about reading a spatial extent. Like I'm only interested in this piece of data. What about reading and streaming temporal data?
So that's where, czar, or like there's a lot of work going on with cloud optimized netcdf, which really uses czar metadata to index into netcdf files. But it's a similar thing, right? There's a spatial dimension. There's two spatial dimensions in a raster in the sort of gridded n-dimensional format that is, what netcdf or czar encapsulates. You're just adding the spatial dimension to. So you're saying this area, this time, find me the set of bytes, and they can be like centrally located or located in a number of files. Just find me those bytes and then read those. So it's really an index into an n-dimensional array of data.
When you're moving these large data sets over from wherever it is they're being stored, hosted today, and bringing them into your environment, I'm assuming you have to convert them into these cloud optimized formats. How do you decide which format to use? Like, what does the decision look like when you're looking at a data set? Okay, should I store this as a cloud optimized GeoTIFF or as a czar? What does your decision process look like? And do you even have to make that decision, or do you just store them as both?
Yeah, that decision process has been interesting in some cases. Sometimes it's really easy. I mean, Landsat comes in cloud optimized GeoTIFFs already, and things that are like really a snapshot of time that is not temporally dense, right? Like a satellite imagery, an individual capture that has a really well-defined footprint on the Earth is just good for raster data. So cloud optimized GeoTIFFs is an easy answer there. However, there's some formats that are stored as non-raster formats, right? And like HDF and netcdf like can store raster data inside them, oftentimes do. For instance, the GOES 16 and 17 satellites, the data that NOAA offers is through netcdf files. And actually the projection information encoded in those netcdf files is pretty tricky because the satellite is so far back, it's taking such a wide picture of the Earth that the actual like footprint of the Earth, quote unquote, can go outside of the circle of the view of the Earth. So encoding that. So when we were processing that data, we're storing the original netcdf because we want to make sure not to make too many editorial or we don't want to make too many modifications on the scientific data that people have been experts in and are offering, right? We want to offer as close to the original data set as possible, but then we exported cloud optimized GeoTIFFs for each of the bands in the CMI, the cloud and moisture imagery product of GOES. And it turns out that those rasters, some of the open source tooling dealing with rasters can't handle the projection information as well as you'd like. And actually that affected our ability to visualize that data. So we also offer a Web Mercator reprojected version of the first three bands, which are used for visualization, just so that you can explore it using our tool to put the images on the map and be able to find the images, actually see the images that you want to use. But when we're making decisions about data sets that are not so clearly obvious to use raster data for, there's a discussion in the community about what is czar good for versus cloud optimized GeoTIFFs versus some other formats. So our take on that so far, basically we have conversations with community members, with the data providers to try to figure this out. And so what we've kind of come across so far is that if you have temporally dense data that you want to actually chunk, you want the individual components of the file to be accessed in chunks of time, then that's where something like a cloud optimized netcdf or a ZAR format would be better. But we do have to make that choice, and we're continually thinking, okay, should we host this in cloud optimized geotiff? Should we host this in another format like ZAR? Is this more of a point cloud data set? Should we host multiple chunkings of each of the data sets? So yeah, it'll be interesting to see how the cloud optimized formats of these data transform, and based on user input, if we end up actually hosting multiple copies or transforming the data to make it more easily accessible.
So I think you've done an absolutely brilliant job of describing the hosting decisions you're making for each data set. Could you talk to us about how you make these data sets searchable, how you expose them to the world?
Sure. We lean really heavily on the amazing work that's going on in the Stack ecosystem, the spatiotemporal asset catalog ecosystem, which is an effort that arose from a number of people who were building out APIs to do this type of work, to make geospatial data available on the web and searchable. And organizations were kind of inventing their own sort of metadata standards or just, figuring out for themselves, okay, how do we encode these similar properties of Earth observation data and other spatiotemporal type data, where a bunch of us met in Denver for the initial Stack sprint before it was even called Stack, and put our heads together to think about what does a implementation driven standard look like that is flexible enough that it's not going to take a long period of trying to nail down a specification that covers every single use case, but instead is something that we can iterate on through GitHub and not be super strict, be extendable, and be implementation driven. And so Stack came out of that, and I believe it's picked up a lot of steam, and people realize that it's a way to just encode metadata for spatiotemporal data, whether it be rasters or point cloud or anything, and have a common language, a common JSON schema to be able to specify, what does this data contain? How much information can I contain about this data? And what that allows, an API to do is then build a database that indexes the metadata for its spatial component, its temporal component, and allow searches over that data, and then have a very well specified return value. So applications, whether they're building against the Planetary Computer Stack API or they're building against the Element 84 Earth Search API, they're getting the same sort of information in a standard way.
Could we draw any comparison at all between Stack and perhaps the GET capabilities request of a web feature service?
Yes, actually. So WFS is being superseded by a standard called OGC API features. And this is part of OGC's new suite of standards under the sort of OGC API umbrella. And so Stack itself is comprised of two different components. There's Stack Core, which is the data models, and then Stack API, which itself is an extension of OGC API features. So they're really not one and the same, but Stack API is a version of OGC API features. It reuses all of the sort of language about collections and items and all of the API specification of how you do searches, the way you specify the query language in the CQL2 language now. So, and the Stack community has been working closely with the OGC API features community to sort of get the standard working in both cases. But yeah, I would consider the Stack API as a specific application of OGC API features.
We've talked about the hosting of data, and now we've talked about how you're exposing this data to the world, how you're making it searchable, how you're helping people find the data that you're hosting. Can you talk a little bit about the Jupyter Hub that you're hosting?
Yep. So, in order for the data to be most easily accessible, give the fastest access, and also, with cloud providers, often if you're moving data across data centers, there's an egress fee that somebody has to pay. So you really want to move your compute next to the data so that it lives in the same data center as the data. And so, there's plenty of ways to do that. The Pangeo ecosystem has like a rich set of documented ways to deploy Jupyter hubs with open source tools so that you can do earth science analysis, data science in cloud environments or on supercomputers, HPC systems. But you have to know how to like deploy that, and it's a pain to manage a deployment of a Kubernetes cluster that lives next to the data. So we provide a service that we're doing the management of the deployment of that system and the maintenance of the images that contain all of the most up-to-date open source libraries, and allow users to request access to that Jupyter hub in which they get an account and they can sign in and use a pod in our Azure Kubernetes cluster that lives in the same data center right next to the data.
So you're talking about I need to apply for an account there. Are there certain pieces of this that are pay to play and certain pieces of this that are free to use?
Everything is free to use. The data and APIs are anonymously accessible, right? You don't have to have an account to access them. You can just go to the public endpoint. There is a token mechanism that you have to use in order to access the data, which is just a way for us to control egress, but it's also anonymously accessible. You just hit an endpoint, you get a token, you can use that token for a set expiration date, and then you just can get another token. And it's a bit rate limited, but it should be enough for doing large scale jobs.
So just so I understand this, let's say I search the stack, I use the endpoints that you're exposing to the world, I search through the data you're hosting, I find something I'm interested in. What do I get back? Do I get back a URL that I can pull that into my own system and then start streaming data from your hosted blob store over to whatever it is I'm doing for free?
Yes. Yeah. So you get it with the stack assets, you get an href, which is a URL. And then so that URL won't work on its own. You just have to hand that URL to a second API and say, hey, sign this. Or you can request a token and sign it yourself, but it's just appending a query parameter to the URL. And so if you found the data you wanted, you have the stack items, you have all of the metadata to say, okay, this is the data that I want to work with. And now there's a variety of open source tools to integrate to turn stack items into, data, either X-arrays or VRTs now with the new release of GDAL. But you would have to sign those URLs prior to accessing the data. So it's just one little step in between.
So by signing a URL, are you talking about getting a token?
Yeah, getting a token. Yep.
So this sounds absolutely amazing. So this means that I could be sitting at home here and I could search your catalog, find some data I'm interested in, pull it into QGIS, for example, and start working on it for free. Incredible. Why is Microsoft doing this? Why is Microsoft providing this service? What's the sort of motivation for Microsoft to do this?
So Microsoft has taken a stance that in order for Microsoft as a business to do well